Notebook, please, Gary. Here we go. So this lesson is titled Finding Time. And it's called that because most of the equations we've been playing with last week involved time, like the time it took Ebola to grow, the time it took your car to depreciate, the time it took a population to grow to a certain point, the time it took an investment to grow to a certain amount. And we can plug in time and get answers. So the hard part is then, well, what if I know what the answer is? How do I get the time that happens? And that's what this lesson is all about. And so we're going to do some possibly new math. You may have seen this before, but you may not. Hang on, my magic board suddenly decided to not work. Come on. Okay, there we go. So we're going to look at solving for an exponent. Before we solve for an exponent, though, we got to review a few things. So let's take, for example, let's see, that Ebola situation, if I remember that right. There was a linear version of that. And I think the linear model looks something like y equals 104, I think was the change per month, times the number of months, plus I think we started at 130. Anybody remember that number? I'm just going to make something up. I'm going to call it 136, but I don't think that's right. Anyway, this is a linear equation right here. It doesn't have any exponents. It doesn't have it's just, you know, a number times t plus another number. And we've solved lots of these throughout the quarter. That's what we did the whole first half. So if somebody said, when does y equal, say, 500, we can solve for t here to make that happen. So we would take the 500 and plug it in for the y, and then we'd get 104 times t plus 136. And I think most of us, to solve this, would first get rid of the 136 because that's the easier thing to do, subtract. And plus 136 minus 136 is 0, so that's gone. So I just, on the right here, have 104t. On the other side, I got to finish that subtraction. So what's that going to give me? 364, I think, if my calculator brain is working today. Yeah, that looks right. And then the last step would be to break this multiplication right here by dividing by 104. So we divide by 104. And then here I have a number divided by itself as 1, right? So that's equal to 1t, which is just t. And on the other side, whatever my calculator says about that is the answer. And so I can go check that. So 364 over 104, calculator, 364 over 104 is 3.5. Well, that came out pretty nice. No crazy decimal. Thank you, universe. So if this was time in months, we could say, well, 3.5 months later, the Ebola population will be about 500 individuals, okay? If we're growing at 104 per month and started with 136. So we could write a whole sentence about that. We could check to see if that works by plugging it back in. So if we take that 3.5 and plug it in for t, multiply and add, hopefully, oops, 136, that gives us the 500 I was hoping. So let's check on the calculator. 104 times 3.5 plus 136. Calculator says 500. I got it right. So we've solved equations like that before. The thing we have to learn to do next is, now that's the linear version. There was an exponential version. And the exponential version looked something more like this. So exponential model. And again, I apologize if I don't have the numbers exactly right, but that's not the point here. Y equals, starting at 136, multiply, I believe it was 80% increase. So we had a 1.8 to the power t. When the t is in the exponent, solving that is much harder. Sort of. We haven't talked about it in this class yet, if the exponent is where it is, right? I can certainly divide the 136 to the other side, So let's suppose, again, I said, hey, y is 500, solve for t. Okay, well, I'd write 500 equals 136 times 1.8 to the power t, and then I would, in this case, I would break that multiplication by dividing. And then I could ask my calculator what's 500 over 136, or I could leave it like that. Fractions are nice. On this side here, a number divided by itself is 1. 1 times anything is itself. So on the other side, I've cleaned it up. I now just have 1.8t. But how the heck do I get that exponent out of the exponent position? Because I want this to say t equals and then stuff on the other side. And so this is what we need to learn right now. That's what this lesson's about. How the heck do we get that t out of the power? So we'll come back to this. I'll pause there in case anyone's writing frantically. You may not have guessed this yet, but I'm very excited about this topic. This is fun stuff. Okay, so again, we will come back to that because we don't have a routine how to do this yet. So, a review of exponents, just a reminder what they mean, and then we'll start solving stuff that have exponents. Normally, if the power is a whole number, it just means write that base down so many times. Like, for example, 3 to the power 5 means write the 3 down 1, 2, 3, 4, 5 times, and then multiply those suckers together. Okay, and then my calculator could do that. If we have a power 0, the answer is always 1. So if somebody said, what's 7 to the power 0? Well, it's 1. What's 10 to the power 0? It's 1. Okay. So that's another one. A rule we haven't talked about, but that is important. You may have seen it before. And negative exponent means flip the base. Okay, so an example of that is if I had 2 to the power negative 1, that's 1/2. Or if I had 10 to the power negative 1, that is 1/10. It even works with fractions. So if I had, for example, 2/3 to the power negative 1, that would be flipped, and the answer would be 3/2. And we could check those on a calculator. So I'm going to check, let's check 2 to the negative 1. And this is going to come up on today's lesson and in future lessons. So this is important. So if I take 2 and I raise it to the power, and I think on my Google calculator I need parentheses for my negative 1. Calculator says 0.5, 1/2. If I ask my Desmos calculator, what is 2 raised to the power? I don't need parentheses in Desmos. It says 0.5. Or I can say, Desmos, make it a fraction, please. Isn't that cute? I love Desmos. Okay, so negative exponent flips it. If I started with, say, 1/2, arrow out, close the parentheses, and raise that to the power negative 1. Anybody want to guess what the answer is going to be? Or Desmos is probably going to tell me. Ah, Desmos, why did you tell me? It's 2. If I flip 1/2, I get 2. So negative exponent just means flip the base. And we're going to have to deal with that in this lesson and future lessons. So if you haven't seen that before, cool new fact. If you have seen it before, hopefully you remembered it. All right, we then played around with graphing multiple times of using an exponent, and we end up with these exponential equations, which I claimed before looked like a hockey stick to me. And if the base is greater than 1, so this one right here, the base, whoa, come on, pen, is greater than 1, I get this increasing graph. It goes uphill to the right. And if I have a base, in this case over here, that is less than 1, then I get this curve that drops down. It's called a decreasing curve. And these are all things we looked at, aside from maybe the power negative 1, these are all things we looked at last week. Quick review of exponents. So don't worry about redrawing those graphs there. Just want to remind you, we've seen increasing functions like compound interest We've seen decreasing functions like car depreciation. This is just a bit more extreme. All right, next, this is the big thing for today. A logarithm is an exponent. So maybe you've heard the word logarithm in a math class before, maybe you haven't, but this is the most important thing for today. A logarithm is an exponent, and I'm just going to give some examples of what that means and how to use it. So here I have an example of an exponent. 10, the base, to the power 2 is equal to 100. Okay, so that should be a fact we're all familiar with. We're going to get used to new versions of these powers rewritten as what are called logarithms. Logarithm is often abbreviated LOG, and every exponent statement has a corresponding logarithm statement. Right? So in this case, I've got 10 to the power 2 equals 100. The related logarithm statement says that log base 10 of 100 is 2. So I'm going to write that down in words, what this green sentence, this green line means here. This says log base 10 of 100 is 2. So that's how I read it. Log base 10. Just like the base of an exponent can be any number, the base of a logarithm can be almost any number. And a logarithm answers the question, to what power do I raise 10 to get some answer? So over here below, I wrote log base 10 of a number equals some power. Right? A logarithm is an exponent. The word exponent is synonymous with power. So one way to interpret this statement, besides just reading it, is this says 10, the base, raised to what power equals a number. So if I put that in math symbols, 10 to what power equals that number in the box there. So we'll play around with a few versions of this in just a minute. And then we'll ask our calculator about it, and then we'll solve some equations. All right, let's see, are we ready for the next page? Almost. Okay. So let's just look at another example. 10 to the power 3 is equal to 1,000. The related logarithmic statement I could write would be log. Since 10 is the base here, 10 has to be the base of the log. Parentheses always come next. On the other side, I got to put the power. Okay. Why do I have to put the power there? Because the word logarithm, if you look it up in a dictionary, logarithm, literally means exponent. So whenever you write a log, on the other side of the equals has to be whatever the exponent was. Okay. The only place for the 1,000 to go is in the box here. So we're going to test this out on our calculator now. So just double check. If I take 10 and raise it to the power 3, I should get 1,000. Now on your calculator, you'll learn how to find a logarithm on your calculator. If you're using Desmos, then you have to go to function, F-U-N-C for function, and then find log, L-O-G there. And then I can type in, go back to main, and I can type 1,000. If you're using Desmos on your phone, it looks a little bit different. Close your parentheses, hit enter, calculator says 3. If I check this on my Google calculator, the log button's already sitting there. It starts the parentheses, so I just type 1,000 and close the parentheses, and it says the answer is 3. All right, so we'll do another one in just a sec, back to the notebook. Let's see, what is 10 to the first power? Anybody? Anybody paying attention out there in the universe? 10 to the first is?
10.
Perfect. So if we wrote this as a logarithmic statement, we would write log. This right here is my base of 10, parentheses equals. The exponent has to be on the other side of the equals because a logarithm is an exponent. This other 10 would have to go inside here. So let's ask the calculator, what is log of 10? Now, note on a calculator, it doesn't have that 10 down there. So on a calculator, that means the same thing as log of 10. So if there's no base, we assume it's 10. Let's make a note of that. No base on a log means the base is 10. So on my calculator, if I type log 10, close parentheses, calculator says, answer is 1. All right, let's try another one on the calculator. We know, for example, that 10 to the first power is 10. We know that 10 to the second power is 100. Can we figure out what power of 10 is 75, for example? Well, 75 is between 10 and 100, so the power should be between 1 and 2. And we could translate that to a logarithm statement. So this one right here we just did, that was log of 10. This one down here would be log of 100. And so the one in the middle must be log of 75. So let's try asking the calculator, what's the log of 75? And that answers the question, 10 to what power equals 75? That's what logs do. They tell us what power for the given base. It gives us what's in the box. So log of 75 is 1.87506. That's a lot of decimals there. I'm just going to borrow, let's say, the first 5, 87506. So if I take 10 to the power 1.87506. Now I rounded the answer, so I'm not going to get exactly 75, but I should get pretty darn close. 74.999, that's not bad. The more decimals I put in the power, the closer I will get to exactly 75. So again, what does log of 75 mean to us? To what power do I raise 10 to get 75? Right? That's this right there. 10 to what power is 75? And we found, according to the calculator, that the log of 75 is about 1.87506, which means if we take 10 to the power 1.87506, then we should get pretty close to 75. If we round to the nearest whole number, we got 75. So logarithms help us find exponents. All right, next. I mentioned this a minute ago that if there is no base written, it means base 10. Because our number system is based on 10, a log with a base 10 is called the common logarithm, and we usually abbreviate it without the 10. So anytime you see log with no base, it means the base is 10. We need to know that sometimes. So log base 10 is called the common log. On a calculator, it's just log. Spreadsheet has a similar version we'll look at later. Now, what I want to do next is I want to use the calculator logarithm to help me solve an equation like this, or like the equation we were looking at earlier. Now, we're not quite ready to do that first one I showed in the beginning of class, but we can do this one right here. So I want to solve this equation right here for x. To do that, I have to try to get x alone, and when we're solving equations, we usually get things that are further away out of the way. So the 3 has to go first. Since it's connected by multiplication here, I'm going to divide by 3. So 3 divided by 3 is 1. 1 times 10x is 10x, or 10 to the x, excuse me. On the other side, let's see, 3 goes into 60, how about 20 times? So this says 10 to what power equals 20. That means find the log of 20. Right? Because what does a log mean? It says 10 to what power is 20. And that's what a log does. On a calculator, it would just be the log of 20. I'll show you a slightly different way to write this in just a moment, but let's check that and see if it works. I'm going to use this calculator here. What is the log of 20? My calculator says it's about 1.3-ish. I could add more decimal places if I wanted to. I'm just going to try 1.3 and see what happens. Back to my paper. I'm going to make a note that my calculator says that that is about 1.3. Now to check to see if I got this right, I just plug it back in and see what happens. What if I take 3 times 10 to the power 1.3? I'm hoping to get close to 60. Now I may need more decimal places to do that, but let's give it a try. So 10, oops, not clear, 3 times 10 raised to the power 1.3 equals 59.857. Now, if I had more decimals, it might get me slightly closer. Like what if I took 3 times 10 to the power 1.301 to 3 decimal places, a little bit closer to 60. So the more decimals I put in that power from the logarithm, the closer I get there. So that's pretty close. That's approximately 60 to the nearest whole number. Now, slightly another way to write this that we're going to need in a moment. Oops, too far. Back here. There we go. So let's take that 3 times 10 to the power x equals 60. Another way we'll go about writing this down, it'll start the same way. We'll divide by 3. And that's going to give us 10 to the power x is equal to 20. And then just like I can divide both sides by 3 or multiply both sides by something, what I can do next is write log parentheses on each side. And it has to go on the left side because that's the way the calculator writes it. So we can, this is what's called taking the log of both sides. And it is really much like dividing both sides by 3 or adding the same number to both sides. The trick here is this is really log base 10. And so this left side says 10 to what power is 10 to the x? Well, it's got to be x, right? So this side always cleans up if the base is 10. I'll talk about that in a different way in a minute. So 10 to what power is 10 to the x? Well, x, 10 to the x. And on the other side, I just need the log of 20. So this part right here may seem kind of magical at the moment, but we'll get used to it. So slightly different way of coming up with the answer I had before. The reason that we need that idea of taking the log of both sides takes us back to this equation we looked at in the beginning of class, right here. So if I want to solve this equation right here for t, I need to use that idea of taking the log of both sides. So I'm going to do a slightly easier problem and then come back to that one later. Let's see. All right, Here we go. So let's suppose I have a slightly different problem. I have 2 times 3 to the power x equals 20. To solve this, the first thing I would do would be to divide by 2. 2 divided by 2 is 1. 1 times 3x is just 3 to the x. On the other side, I have 2 goes into 20 10 times. Then I apply that strategy I went over a minute ago where I write, I'm going to take the log of each side. And when I do that, another trick, like if that's not a 10, I have a problem. It turns out the power can jump out. So a power in a log jumps out as a multiple. So this is an important idea that we're going to need for the last part of lesson 4.3. I had the log of 3 to the power x. That x gets to pop out as a multiple whenever it's inside of a log. Now I have x times the log of 3. The log of 3 is just some number. If it's just a number, I can divide by it. And so when I divide by it, I get log of 10 divided by the log of 3. Now here we have to be careful. I cannot simplify this unless I use a calculator. Okay. So a lot of times in algebra, we're used to doing things like seeing something where we have a fraction, and then we go and say, yeah, let's cancel stuff because we love crossing stuff out, and say the answer is 10 over 3. This is like super bad. Super wrong. That is not true. The best I can do is type that into the calculator right there. Right? So let's test the calculator to see if that actually does solve that equation up there. So I need to take the log of 10 divided by the log of 3. So log of 10, and then I have to close the parentheses for the log of 10. Then I can divide by the log of 3 and close the parentheses there. Okay. So I'm just retyping what I wrote in the notes when I divided by the log of 3. So log of 10 divided by log of 3, parentheses are super important. Enter, or equals, I get 2.0959. Let's say we went for 4 decimal places, 2.0959. So I think this is about 2.0959. The only way to be sure that that's the answer is to plug it back into the original. Otherwise, it's just a wild guess, maybe an educated guess. So then we have to take that number and plug it back into 2 times 3 raised to the power, and so it's 2.0959, and I missed a digit, 959, and hopefully that comes out to pretty close to 20, and that's pretty darn close to 20. Sometimes the answers will be a little over, sometimes under, it depends on the rounding that happened. Okay. So it turns out it does check. So 2 times 3, so this is my check, to the power 2.9509, oops, nope, wrong order, 0959 is about 59.9999. That's pretty darn close to 60. So we got to get used to what a logarithm is. We got to get used to how to type it into a calculator, and we've got to get used to how this crazy step right here works, where we take a log of each side and pull out a power. So those are the big goals for today. All right, and then after we play with the lesson, we're going to come back and look at some interesting problems in the prep. So into the lesson we go. So we've already kind of started the lesson here. I've gone over several problems that are actually in the lesson. We're going to jump into groups and see what happens. So like I mentioned before, we are solving equations. So they give an example of solving an equation here. But we're trying to do it when we have exponents or powers, and that involves logarithms. So that's just the intro. I've talked about that, but you should read this yourself. Here we're playing around with kind of how to use a log on a calculator, how it relates to powers of 10. So let me blow this up and I'll do a demo, and then I'm going to set you guys free to work. The first example says the log of 1,000 equals the log of 10 to the third. And this is true because 1,000 is 10 to the power 3. And a logarithm says, hey, what's the power of 10? Well, the power of 10 is definitely 3 right there. So the answer of the logarithm should be 3, that power. 100 is 10 squared. So here I would put 10 raised to the second power. And a logarithm says, hey, what power of 10 do you see there? Well, I see the second power of 10. So I would put a 2 there. Okay. So what we're doing here is we're taking the inside of the log, writing it as a power of 10, and then the answer, according to my calculator, better be that power. Okay. And so you could double check these on the calculator too. All right, group time. How many people do we have today? We have 13. Let's go with 4 groups. And I think that looks pretty good. All right, jump in a group, start working. I will stop by shortly to check on you.